Hello again. If you haven't watched my video on fundamentals of trigonometry, please watch that video. It will tie up nicely with the second video because this is actually a playlist of videos on on fundamentals of trigonometry. Um, so starting from fundamentals up to until grade 12 syllabus. So now that you have an idea of what fundamentals, the background of trigonometry and fundamentals of trigonometry, the second objection that I want to be looking at is getting a proper understanding of the basic concepts. So we are going to try and derive almost everything from first principles. Um, Now, we are going to expand these two angles here, and we're going to look at something called similar triangles. So similar triangles are very nice angles. Um, for now, their definition though will be very elementary. Then once we get into geometry and all the stuff, then we'll start looking at their definition in a more mathematical manner. And then we'll go deeper into what they really mean. For now, we'll just touch up on top, and I hope you do get the concept. We'll try and explain them as elementary as we can. So let's first look at them at this triangle. So we're going to call this triangle triangle X, and then we're going to call this triangle triangle Y. So we have triangle X and triangle Y, and then we're saying similar triangles are triangles that have got the same shape, but their sizes might vary. Now, what do we mean by that? The shape, of course, all triangles have got the same shapes. They have got three sides. But then what do we mean exactly by the same shape in this context? What we mean is that, in a sense, all the sides, the angles inside them, and the slanting of their sides is exactly almost the same. Now you get an idea as to what I mean about that. So you remember that you talk about an angle, and you said an angle measures separation between 2 points, between two lines that are meeting at the vertex or a corner. So that's an angle. Now, how would we say that these two lines like this that form this open shape, like this open two-sided shape? How would we say that this is exactly similar to this other to the second open-sided shape? This will only be similar if that angle, that theta 1, is exactly equal to this angle here, which is theta 2. So in the sense, they would be similar if theta 1 is exactly equal to theta 2. Now, the term that is mostly used in this is to say that these two angles are congruent. Now, the term congruent means in harmony. So it means things are agreeing, they are in harmony. So in harmony or agreeing. So in a sense, equal. I like to use the term equal, but you'll hear a lot of congruent as we move further and when we get deep into similar triangles when we're doing geometry. So for now, in a sense, then I'm trying to explain what we mean by shapes. This shape here and this shape here are the same because these angles are exactly equal, which means that the opening of that line and opening of this line, and also this length here, which we're going to call length B, and that one we're going to call length A, and then this one we're going to call length B2, and that one we're going to call length A2. So these lengths also, they must be exactly equal. In these lengths here, in the sense, for this to be exactly the same, they must be exactly equal in this sense. Now, in this case here, the sizes here are varying. So we're saying that the sizes are varying in the sense that this triangle here is smaller than that one, but the way in which they are shaped and the way in which they are orientated is exactly the same. So but then how do we show that it's exactly the same? This concept here is going to be very important when we're talking about theta 1 and theta 2, because for these here to be exactly the same, these angles have to be equal. Now, these lengths can also be equal, but then it's not very compulsory. In a sense, they are exactly the same in appearance if these lengths are equal, but this length can be longer on that side, and that one can be a bit longer than that one. These will still form similar shapes. Why? Because their orientation is exactly the same because where these lines meet, that angle and that angle are exactly equal. So this is the most important point that I want you to take about similar triangles. So this is what we're saying also here when we talk about the similar triangles. We're saying, well, these triangles, their orientation is exactly the same. So, but their sizes, they are varying. This is a very important concept. And if you don't understand it, please write a comment below so that we can explain it even further. So, because this is where all our concepts going forward are going to be developed. So then we can now look further into this. So if we're looking further into this, then the same we have triangle x and triangle y. And then in triangle x and triangle y, we have that angle there. We have that angle there, which we are going to call it angle. We're going to call it angle theta 1x, right? And then that one we're going to call it angle theta 1y because it belongs to y. And then that angle there we're going to call it angle theta y2, and then this one here we're going to call it angle theta y3. So here we have theta x3 corresponding with that, and then here we have theta x2 corresponding with this one. Now this angle and that angle are exactly the same. This angle and that angle are exactly the same. That angle and that angle are exactly the same. That's what makes these triangles similar. But the sizes can differ. They can be different. Now, to make sure that you understand this point, I'm going to ask you to do something practical. But then in the meantime, wait, you're going to, because I want to also explain something. We also have the ratios of this side. So we talk about the angles and then we talk about their ratios. We're saying the angles are congruent. The triangle, the angles are congruent. And then we're saying the corresponding sides are equal in proportion. And if you look here, we are saying that AB over BC is exactly equal to DE over EF of this triangle. So even if you take this combination, even if you take AB over AC, it's still going to be equal to DE over EF, or whatever different kind of combination you take is always going to give you equality of proportion. Now, you don't have to think much about where this comes from. I'm going to get to this when you get into geometry. For now, I just want you to make sure that you understand that concept, that because of these angles being the same, then that condition is going to be true. That's what similar triangles are all about. Now, let's get into this idea. Okay, maybe let me write this down also. We are saying theta 1x is equal to theta 1y. Theta 1, so theta 2, so theta 2x is equal to theta 2y or y2, whatever way. Theta 3x is equal to theta 3y. So all these angles are the same, and only if these angles are the same will that condition of those ratios be met. So this is very, very, very important. This is what we call similar triangles. Their shapes are not necessarily the same size, but because they meet these conditions, in a sense, they are very similar to one another. Now, they're not right angled triangles, they're just triangles, two triangles that are similar. They don't have to be right angled triangles, even though we are necessarily dealing with right angled triangles. Now, we are going to go to our actual triangles, which are right angled triangles. Now, what I want you to do is I want you to do something practical here. So we're going to do a practical experiment. Let me see if I can get another color there. Let's get black. So we're going to do a practical experiment. So in this practical experiment, I want you to take a protractor. If you do have a protractor, draw a straight line. And then from that straight line, draw the straight line to be, let's say, 20 centimeters. And then draw another straight line this direction, then make that straight line 30 centimeters. Oh no, don't make it 10 centimeters, make it 10 centimeters. It's going to be too big. And then make sure that this angle here is 90 degrees. If you have questions on how to make sure that angle is 90 degrees and how to use the protractor, you can post a question here below and I'll be able to assist you on how to use the protractor. I'll do a video on that if there are requests. But make sure that this angle, these lines here, they meet exactly at 90 degrees. And then what you can do is that you can then do something very special. Connect these 2 points there once you've done that. So you measure these, you make sure that they meet at 90 degrees, connect those 2 points there. Then go again and make another triangle. The same here, it's 90 degrees, straight line up, and then they meet there. But now in this case, this is 10 centimeters, and then this is 5 centimeters. And then that angle there is 90 degrees. If that angle there is 90 degrees, then and you drew exactly a straight line, those angles there are going to be 45 degrees, and this angle here is going to be 45 degrees. That angle there is going to be 45 degrees, and this angle here is going to be 45 degrees. Now you've learned another basic law of triangles. Why are we saying those angles are 45 degrees? Is because if you add up or do what is called summing of interior angles, of all the inside angles, we call them interior angles of a triangle, then they're going to be equal to 180, always, all the time. This is just another nice intrinsic behavior or property of triangles. Now that we have done this, now that you have done this experiment, now remember that because the angles here are similar, this angle is equal to that, this is equal to that, this is equal to that, these sides here, we say they are similar, even though these are not the same. That's why we are saying the shape, that's why we are saying here, triangles that have the same shape but their sizes may vary. So because of these angles, their shape will be exactly the same. That's why I said use 90 degrees there and here use 90 degrees. Otherwise, if you use 70 degrees here and here use 90, then their shapes are not going to be the same. But then now we want the shapes to be exactly the same, but the sizes to vary. And that's what similar triangles are. And if you take, in a sense, if you say this is side A, B, C, and then say D, E, F. If you see here, remember we said that for these to be similar, AB over BC must be exactly equal to DE over EF. Now, if you look at DE, what is DE? We said DE is going to be 10 centimeters. DE is 10 centimeters, this here is 5 centimeters. And then there, right there, DE is 20 centimeters, this one here is 10 centimeters. So if you divide these sides, then you get 2. So which means this is going to be exactly the same. So in a sense, you're having here something like 20 centimeters divided by 10, which is equal to 10 divided by 5, which is equal to 2. So they're exactly the same, their ratio. Now, you could say that we developed this in a very bad way because we gave these values, right? But then, if you want to make it special, go and do this triangle, make it 90 here, then don't measure this here, don't measure also this side here, just do a triangle, just go and do this, another practical experiment, so that you don't keep the values yourself. So you're going to go and write, measure this line, and then draw a straight line like this, make sure that they meet at 90 degrees using a protractor, and then join those. Now when you're joining those, don't define these sides. Don't define the sides. Go again, make a bigger one. Make sure that they are bigger. This one is bigger than this one, and then make that angle 90. Then don't do anything. Go and measure this, go and measure that. You'll see that this will be 45, this will be 45, and that will be 45, and that will be 45. And then go and measure this side. I'm telling you now, before you even go and measure them, this side here will always, this side here, AB, C, this side AB divided by BC will be exactly equal to this side DE divided by EF. So what you're going to do in this case is that you're not going to specifically write the sides by yourself. You're just going to draw something, draw a line up, and wherever you want to end, draw a straight line this side, and wherever you want to end, make sure that they're 90 degrees to one another, join those lines together, do a similar thing, just make sure that the sizes are not the same. So that line is longer than this one, and this one is longer than this one, and then connect them together. As long as the angles here are 90 degrees, those will be 45, 45, and as long as the angle here is 90 degrees, and those two there are 45, 45. In a sense, they do not even have to be necessarily 45, 45. They'll only be 45, 45 if you make these lines equal, in a sense. So excuse me on that one. They'll only be 45, 45 here if you make these lines here equal, because that's what we call an isosceles triangle. So that's a mistake, that these angles here will not necessarily be 45. They can take any form depending on what you write here. But in a sense, once you're done doing that, when you come here, this side, I want you to make these angles 45 now. See, so you measure this, and then you turn around your paper and you draw that line there, but you make sure that the angle between this and this is 45, then the third one will be 45 automatically. Also that will be 45 automatically. And then once you're done doing that, once you're done doing that, you're going to measure this side, use your ruler, because remember you drew this side intuitively. So measure this side, and then also measure this side, and then go and divide them. Measure this side, go and divide them, and you will get exactly the same answers. This here, when I'm highlighting it again, it won't be 45 and 45. It could be any different types of angles, not necessarily 45 and 45, because these two sides are not the same. If they were equal, then these angles would be 45. In a sense, to make sure that you get that 45, you can make them equal 20/20 or 10/10, and then when you come this side, because you're just doing it intuitively, you can't make them equal. So in a sense here, you will make them equal 10/10, you will make them equal 10/10, 20/20. And then when you're coming down here, you won't make them equal. You just draw this side, and then draw that side, and draw this side, and draw this side. And then the angles now there won't be 45. They will be different. So you no longer have to make them 45. You can make them 45 there only because these sides are equal. Then we're still going to go to properties of triangles, but it's going to be when we're doing geometry and looking deeper into different types of triangles, where we're going to also be looking at similar triangles. So in a sense, this is what my introduction into similar triangles, and this concept here is going to come in very handy. We are going to repeat it again when we continue with similar triangles, but then now looking at this here, the more 90-degree triangles, and then deriving our trigonometric ratios and trying to see where those trigonometric ratios come from. Where do you get a sine, a cosine, and tangent? So this is going to be it for this video. Hope you enjoyed it, and don't forget this fact here and this fact also in this position. Thank you.